User authentication is different from message authentication in slight few ways. For example, users have thumbs and eyes, and which messages don't. So we can authenticate you by things and different than the message. So here we will talk about 5 different things. First of all, how do you authenticate a user using secret keys, and 2 systems that are used are Kerberos 4 and Kerberos 5. Then we talk about how to authenticate using public keys, and then federated identity management, which means that you are authenticated here, but you can use it over there, some other place. So the thing about the users is that we can authenticate them by something that they know, just like your PIN and password, which is the common method, or something that you have, which is like some people have those token things, that they have a credit card. We can authenticate that, yeah, you are you, if you have that credit card. Or biometrics, which is fingerprints, or iris, or something that you do, such as speak or sign, right? So these are all 4 possibilities, and all have some issues or the other, right? For example, biometrics do not always work. I mean, for example, we have this fingerprint thing reader on almost every computer. My computer has a fingerprint reader, but some days it doesn't work because my finger had a scratch or something like that, right? So I have to go back to password. So and the tokens can be lost, credit cards can be lost, and the voice can change if you have a cold. And so sometimes people use 2 of them. So I've seen people who work, for example, a friend of mine works for RSA, so he always carries this thing, smart card, and then obviously he has a password, and maybe I don't know whether they look at his iris also. So there are several things they use in combination. But second thing is that the authentication could be one way or mutual. And it's interesting. When we started all this security stuff, it was always one-way authentication. So the users identified to the bank, and the banks didn't authenticate to the user. It was not felt necessary. The users identified to the base station, and a Wi-Fi base station, but the base station did not authenticate to the user. Now you can see what problem that can cause, right? A fake bank can come in and say, okay, log in, please give me username and password, right? And you never know that this is a fake bank or the real bank, right? So now they have started bank authentication. You know how they do bank authentication? By flashing a picture which you selected before when you signed up for the account. If that picture matches, then you know this is the bank. Has anybody seen that picture? Right? That is the bank authentication part. Because if I create a fake bank, I don't know your picture, the picture that you selected. You selected an elephant and I show you a dog, you know that this is not the bank. Right? So be careful with that picture. Make sure that this is the picture that you selected. Alright, that's the bank authentication. And your authentication is the password. And so you don't put your password until you see the bank's picture. And that's why it is 2-step process nowadays. Okay? Alright. So it could be one way or mutual, and in some cases it has to be one way, like email. If I send you something, it is only one way. I mean, I'm going to send it to you and hopefully it will reach you. And when you get it, then you will want to know whether it came from Professor Jain or somebody else sent it. So it is only one way, the sender authentication. Right? If the receiver is wrong, then hopefully I would have done it in such a way that nobody else can read it. Alright, so it can be, what kind of attacks can be? First is replay attacks. And this is not a complete list again, but it is an example list. Somebody could simply replay things if there is no timestamp. They could just play the message again and again and again, and it will look like the original message. If it is time-stamped, but if the timestamp allows you an error of 5 minutes, somebody could play it within 5 minutes. And or somebody could replace the original message with a new message, or somebody could play it back to the source. So source sends a message which is encrypted with a session key. Now the attacker doesn't know the session key, but it sends it back to the source, and source gets the message which is encrypted with the session key, and it decrypts it, and unless the source is really dumb, so figure it out that it is going from me to them and not them to me. But in some cases it could be confusing. So those are some examples, and not the exhaustive list of kind of replays. And so some of the things that people can do is put the sequence numbers. So most of the times we will have nonces, so that we can match, that this is the request, this is the response to that same request, and so on and so forth. Or we will have timestamps, so that if we get it again, but the timestamps are a problem. We need synchronized clocks, and the clocks are not synchronized. Right? And the third thing is challenge response. Oh yeah, first is sequence number, second is nonces. So sequence numbers are kind of not reliable, because computers crash and we forget the sequence number. So it's just better to use random number, which is nonce. All right, so the whole field started with Needham-Schroeder protocol. And Needham and Schroeder came up with this idea that we should have a KDC, and each user registers with the KDC, just like we did before. And so it says, hi, I am A, I want to talk to B, my nonce is N1. And this all goes in clear. Now everybody has registered with KDC, so A has registered with KDC, and KDC knows A is a key. And so it sends a message which is encrypted. So this was the notation we used last time. Encrypted with what key? A's key, KA. And inside the encrypted field we have KS, ID A, ID of A, ID of B, your number N1. Then another encrypted message which is encrypted with KB, right? B's key, and that has a KS session key and the ID of A. All right. So this whole, okay, so these are not two, I'm sorry, this is not inside encryption. Let's see. If I read it carefully, these are two encrypted messages side by side, not one inside the other. There could be one inside the other, but the one inside the other is less desirable, because you have to encrypt a lot many more words than you have double encryption, right? So double encryption is a negative. So anyways, here it is one beside the other. Anyway, so then once A gets it, it can decrypt this thing. It can decrypt what? It can decrypt only the first part. It cannot decrypt the second part. So what it does is it sends the second part to B as it is. It doesn't know how to read it, but it sends it the whole part to B. This is called a ticket. This is like your theater ticket. Once you have it, you can show it to the gatekeeper, which in this case is B, and B can decrypt it and know that the session key is S and this is coming from A. So it can say that, okay, prove me that you are A by sending a nonce N2. If this is really A, then it should know the KS by now, the session key, and it can send it back N2 or some function of N2 and prove that, yeah, it is A. So now both of them know KS. And so this is very strong, except that after the paper was published, some people said, well, there is an attack, and that attack is that somebody can replay 3. So we have a ticket and we can use it again. The only problem will be that what if N2 is so it sends an N2, it will get this thing, and then B will send some other N2 it will not be sent to A, it will block, and then it will somehow be able to act as A, and I don't understand how it can find KS though. But there is a problem here that if it replaces that and blocks, okay, let me just take a chance here and see if everything is okay. Yeah. Okay. So block, so replace 3, block 4. Here is my nonce. It has to know KS somehow. So I think the assumption here was that if someone can crack KS, one KS, any KS, then it can replay that particular ticket many times. Even though it doesn't know KB. Alright? Because to respond here, all you need to do is KS. Whatever N2 comes back, it doesn't go to A, it goes to C or the attacker, and they can figure out N2 and then return N2, whatever needs to be returned. So then they can start acting like A from that point onwards, just by knowing one KS. So then 2 people did modification. First person was Denning, and Denning said we will put the time stamp, and that fixes it. However, the problem with the time stamps needs synchronized clocks, which are not possible. So somebody else fixed it, and they put a nonce along with the time stamp, and so now the time stamps can be looser. Looser means loose. They don't have to be very tight. And so now this is the final. These 4 messages actually, 1, 2, 3, 4. This is the final protocol. Let's start with the first. Here it says, hi, I am A, my nonce is NA. This goes in clear to B. B goes to KDC and says, hey, A wants to talk to me, and the time is TB. And it sends this NA and IDA encrypted with its key to KDC as well as clear. So then KDC sends to A directly. So says a step where KDC sends to B and then B sends to A. So KDC sends to A directly the KS and the time, and NA is the nonce, and then B is nonce. And then A will have to respond back to B with its nonce, and so that to prove that yeah, I got it and I know that I am A. All right. So now, even though there are time stamps TB, but it could be off by an hour or something, but as long as an A and B match, it's fine. And then they had an optimization where once this thing expires, we don't have to go to KDC to find another KS. Just before the KS expires, we can talk to each other and get the next KS. By here is the previous ticket from KDC with my new nonce. You give a new number, N prime A, and then it gives the new number here, and then it returns the new number there. It returns the previous number, N A prime here, and this one returns N B prime there. So by that handshake, they can each re-authenticate again and then use a new key. All right. So now for email, if you want to use this scheme for email, which is one way, and we assume that B is not up. When we are sending the email, B may not be up, A is sending to B. So it says, hi, I am A, I want to send an email to B. My nonce is N1. So it says ID A, ID B, and N1. Then KDC could send the session key, KS, and a ticket. Now this ticket looks like double encrypted. Okay, and I don't see any reason for double encryption, but as stated here, it is double encrypted. So the nonce comes back, that proves that this is not a replay, and this ticket is somehow extracted by using KA, and then the ticket and the message is sent to B. So this message is encrypted with KS, and that KS is encrypted with the KB here. Alright, so the message has both the key and the message, encrypted message. So because it encrypted with KB. By the way, every time I use a single letter subscript for keys, that means that is the secret that B has registered with the KDC. Okay, so KB is the secret that B has registered with KDC. That is the key, that is the master key for B. And similarly, KA is the master key for A. These are all pre-registered, and after that they will use KS, the session key. And this modification was important, the bottom modification, because we, well, see, I was going to say that we use less master keys, but we use only one less master key because we are still using KB, we are not using KA anywhere here. So, there is less use of KA, the less master keys you use, better it is, rather than going through the original process, which has two problems. Not only that you need KA, but you also need KDC to be up. Alright, so that brings us to an interesting system called Kerberos. Kerberos is the name of this three-headed dog. Greek mythological character, which could be called Kerberos, and this is a dog of Hades. Hades means hell or heaven. Hades. 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 I think it's Hades is what? Hell or heaven? Hell. Okay, so he is the dog which is, guarding the hell. Why would they want to guard the hell? I can see that you want to guard the heaven. No authorized entry here. But anyway, so the Greeks wanted to guard the hell, and so this is the dog, and so this is the protector for the MIT's system, basically. So this system was started at MIT, and actually the people who started this thing, all of these were my colleagues because they were working for digital. And in fact, the whole Schroeder company that we mentioned the name, they're all digital employees. So anyway, so designed originally for Project Athena at MIT. So they designed a system, and MIT basically solved this problem, which we all now use everywhere else, is that they didn't want people to log in every place separately. You go to this room and then you log in a different computer, you go to this room and different computer, you log in again, and you have 15 different passwords. So they said, let's just make one place. So they started this system, Kerberos. So Kerberos is freely available from MIT. Version 4 is available. Version 5 is a standard called RFC4120, and everybody uses Kerberos. Windows 2000, XP, Server, Vista, they use Kerberos. Apple, Mac, OS uses Kerberos. Apache, Server, NFS, OpenSSH, you name it, uses Kerberos. So it is designed to protect against eavesdropping and replay attacks, and uses the KDC. Actually, we will call here authentication server, and I will tell you in a minute as to why it is called authentication server. And symmetric key means secret key. So first three versions are no longer in use. Version 5 is a generalization of version 4. Version 4 was designed just for MIT, and I mean actually not for MIT but something like MIT, and now we have generalized it so anybody can use it, version 5. So we will explain version 4 first and then we will go to version 5. So this is how it works. They divided the KDC into two parts. First is called authentication server, another one is called ticket granting server. Authentication server is the one that keeps your secrets. That has to be really put under lock and chain. That's very secret. But once you have your, the other part, like the KDC was giving you tickets, that doesn't have to be kept in a lock and key. Okay, so that was taken out. That was taken out, and that was called ticket granting server, TGS. So you could put all of them in one box and protect it, doesn't matter, or you could put in two boxes. All right, but the functions are separate. So first you say, okay, here is me, and I would like to use the network today. And so then it gives you the authentication server, authenticates you. Basically, you will send your password or whatever it is. They will say, all right, here is your day pass, whole day pass. So then you will go to ticket server and say, well, I want to print right now, and here's my day pass. So then we will give you a ticket for the print server, and you can talk to the print server, back and forth, back and forth. Then you want to go to some other server. You don't have to go to the authentication server again. You can use that day pass whole day for different servers. You want to log in here, you want to log in there, you want to do this, you want to do that. So you go to authentication server, you authenticate in the morning, and you are done. All right, and so they invented this long-term ticket. This is a long-term ticket, and this is a short-term ticket. Right, so they broke this into two pieces: a short-term ticket and a long-term ticket. And so you authenticate once, and then you can use it for many times. We will continue from here next time.